we'll talk about the random walk process. Okay, now we are interested in the stochastic trend, and one of the special case of stochastic trend is random walk process. And when is that going to happen? When the psi takes a value of 1. Okay, so how do we define? A random walk is defined as a process where the current value of the variable is composed of the past value plus an error term. Okay, so there are two important things in a random walk series. You have the past value term and the error term, nothing more than that. So yt is the current value, it's just the past value plus an error term at. So this is typically also known as white noise. Okay, um, where you have zero mean and variance of 1. Okay, so in such a case you will not be able to use time series. Okay, for white noise there's no point using time series. There's nothing can be done for time, in a white noise series. Okay, so just avoid using anything for the motivation behind understanding random walk process. Well, when you have a time series data and you find out that it's following a random walk process, then you stop there. Okay, so that's basically a check that one needs to do before even going for other forecasting, using other forecasting techniques. Okay, so if you plot a random walk process, it looks something like this. Okay, it looks very weird. There's no trend at all, there's no pattern. So basically what random walk means is that there is no pattern in the data. There is no pattern in the data, just pure random. Okay, and there's nothing in the data that you can use for forecasting your future, something similar. Okay, so this is also for typical random walk process. Okay, so random walk process can be closely related to the behavior of stock market. Stock market also many times information in the past values. Although many people will say that forecasting stock price or return is very much possible, but that's not always the thing. Stock market many times behaves purely as a random walk. Sometimes it has some pattern, but many times it has no pattern in it. It's also used in understanding Brownian motion in many science areas, also in finance. A movement of a drunken man, somebody who is drunk, you will have no pattern. If you try to understand or study his pattern of walking, there's no pattern at all. Okay, so it's also a limiting process of an AR1 process. So AR1 process is just yt equal to yt equal to phi y minus t plus at, right? So this is an AR1 process. So when phi equal to 1, you take a random walk process. Okay, if phi is less than 1, you have the AR1. Okay, so this is a typical condition for AR1. So random walk is basically the special case of AR1 where you cannot go ahead in building a forecasting model. So what the implication? What is the understanding or the takeaway point? The takeaway point here is that the implication of a process of this type is that the best prediction of y for next period is the current value. Okay. Now, if you have a time series data and that follows random walk, just stop there. Don't have to do anything. So you all need to convey, you need to communicate to the audience is that the best prediction for this particular time series for future is nothing but the current value. There's nothing more can be done other than that. Okay, it can be shown that the mean of a random walk process is constant, but the variance is not. Okay, so mean of the random walk in many situations it can be constant, but variance is never the case, and that's why random walk is a typical case of a non-stationary series. But many non-stationary series can be made stationary, and you can do forecasting for future, except in the random walk process. That's where the difficulty is. Okay, sometimes you could have a deterministic component to random walk also, and we call that again as a drift. Okay, you have a constant term to it. Okay, so instead of just yt equal to yt minus 1 plus the error term, you could also have something like theta. Okay, theta naught. Theta naught is just the drift. Okay, so this is the deterministic term and this is the stochastic term. Okay, so it will be partially deterministic and partially stochastic in this case. So it doesn't start from 0, right? It starts somewhere here. So that's the drift. So this is the theta naught, and then there's no trend at all. Okay, so it has some deterministic part and some stochastic part. Okay, so this is the typical case of random walk with the drift. So how do you remove the trend, okay, from a series? A series containing a trend will not revert to long run mean. Okay, so if a series has some kind of a trend, it is either upward trend or there is a lower trend. It is never going to, let's say, come back to the mean. Okay, so this series something that you can't expect. But that's what is needed for forecasting, right? So the usual methods for eliminating trend is detrending and differentiating. Okay, either you detrend or you difference. I'll briefly talk about it, not in detail. So here is the case of differentiating and how you make something stationary. So okay, so if you take a random walk, okay, so a random walk is yt minus 1 equal to your error terms. Okay, sorry, this is wrong. Yt equal to yt minus 1 plus your thing, right? So this is a typical case of random walk. Here at will be non-stationary. So in this case, this is a typical non-stationary case. But if you take a difference of that, it is likely to be stationary. If you take the first difference, it is likely to be stationary. So this is where we need to understand what is known as an unit root test. So the name suggests unit root means we are only talking about how to find out whether the phi that we talked about in the non-stationary series is 1 or not. Okay, so in a stochastic trend series that we have just learned, if phi is 1, then we are sure it's a random walk process, and that's what we call it unit root, and we need to statistically test that before getting to know. So when we have a stationary system, we know for sure that the effect of any shock that is going to happen to the time series will die out gradually. Okay, in a stationary series, if you have a shock, it moves up, it eventually comes down, and then it removes somewhere in the mean, and then even if there is a shock in upward or whether it's downward, if there is a downward shock here, it will again come back. But that's not the case in non-stationary system. In non-stationary system, if there is a shock, okay, if something goes up, it never comes down to the mean. Okay, so it never approach the long run mean. Okay, so that's one aspect of uh, you know a non-stationary series, and from there we can derive some sort of a clue as to how we can find out if there is presence of unit root. That means whether the phi is 1 or not. All right, so there are two types of non-stationary. Okay, one case where you have the this case is just 1, and the other case is phi is greater than 1. Here we just taken beta, just keep changing notations. But the second case we of course will ignore for here. So the first case we would like to see when is the case when we have the phi equal to 1, and that we can get to know using Dickey-Fuller test. Okay, so this is a test using which we can find out whether there is presence of unit root or the time series is unit root or not. So unit root is just another way of saying that whether it's a random walk series or not. All right. So the simplest approach is just to have a air one series, okay, yt with the theta, and you have psi of yt minus 1, okay, and we would like to know if psi is sorry is if phi is 1 or not. Now this is AR1 series, right? And we expect phi to be less than 1. If it is equal to 1, then that's a problem. That's a random walk series, right? So the hypothesis testing in the case of a decouplers test is like this. The modulus of phi is either 1 or modulus of phi is less than 1, which is the alternative hypothesis. Either this will get accepted, or we'll just reject null hypothesis, right? Depending on what the test statistic value is. We can rephrase this to make it better, right? Because in a t-test we essentially compare it with the 0 or non-zero, right? So we'll make it more simpler. So how you do that? You just subtract the previous time series from it. Okay, so we have yt equal to yt is theta theta 1, let's say, minus phi 1 yt minus 1. Sorry, I think we have done something else. Okay, so we have the series yt equal to yt minus 1. This is theta naught plus at, and then what we do is that we simply subtract yt minus 1. So from left and both right, yt minus 1 equal to theta naught, sorry, phi, this is theta, sorry, theta naught plus yt minus 1, which is again phi here, minus yt minus 1 plus at. Okay, now this is just delta t, right? So delta yt is equal to theta naught plus, here we can take yt out, so yt, then inside we have 1 minus phi plus at, and then 1 minus phi we just denote with some other symbol. Okay, so so this particular term, if it is equal to 0, then we have a unit root, otherwise not. So it has now changed. Okay, so null hypothesis is now either it's 0 or it's less than 0. Okay, so just slight change. Here we are comparing with 1 or less than 1. Here it is either it's 0 or less than 0. There are three types of decoupler test we can do. I'm not going to the details of it, but depending on the kind of random walk we are trying to understand, we'll have different type of decoupler test. The first case is a pure random walk. There is no drift. There is no theta term here, right? It's just the past value of yt. Okay, so we would like to know if the coefficient is 0 or not in this case. The second case, we have a drift. Okay, and in the third case we have a drift, and we also have a deterministic time component. Okay, we have theta 1 t, so time, right, it's the deterministic trend, so it's just a combination of deterministic and stochastic trend. Okay, linear time trend. Okay, so there are three types of decoupler test we can do depending on what type of what the intention is. I mean, we can also do all three and see which one is actually is the best for the given time series data. So how do you find a test statistic, and how do you do that? Right? You just apply OLS. You have the equation, regression equation. You just find we just estimate the parameters. So parameters here is phi, right? Remember it's 1 minus phi. We just change it to different symbol, but ultimately we are trying to find out what phi is. So we can find that out using OLS, and then we can find out the t statistics. Okay, we can find out the t statistics, and then we see whether it's significant or not given for a given particular value. Okay, so that's how you will get to know if a particular time series is a unit root case or not. And if that is the case, you will be able to find out whether it's a typical random walk or not. In such a case, the limitations of time series methods won't allow you to, let's say, forecast future, you would rather take more of a guess depending on the past values of the time series, rather than doing some sort of analysis that is not going to give any accurate result. So that's one of the important tests that people do before even starting to explore other time series models for forecasting. And it's quite important early enough. If you get to know if a particular time series is random walk, then you do not go ahead with any of this sophisticated methods. You will be saving a lot of time in doing that.